we now have Mark McCurry, who's going to talk about finding real-time safety bugs through static analysis. We'll have two presentations in this session. The next one will be by Winfried Rich. So here's Mark.
Thanks for the introduction. I'm here today to talk about my work on a software project called Stoat. And this project is focused on trying to make real-time software development and maintenance easier. So first off, a little bit of history on the project. It started out when I was maintaining the Zined SubFX synthesizer. And historically, Zin has had some issues with low latency environments. And at the time when I was working on a prototype for Stoat, that was probably the primary user complaint. So trying to investigate this, I could take a look at it a number of different ways, but I kind of wanted a more rigorous approach. So in order to identify what issues were present, I came up with a prototype for Stoat, and it was used to help identify what sort of problems existed within the code base, and it really helped locate them quickly so that they could be patched up. And in the end, overall low latency performance of Zined SubFX has improved considerably. And I've had several users communicate that fact after sending out a few of the updates, which are based off of the information that Stoat has provided. So let's get into what exactly real-time means, what are X-runs, what are all these problems that people end up encountering. Anyone in the audience who utilizes Jack, I'm sure, is familiar with running into X-runs, the unpleasant pops and hisses that you're going to experience with Jack. And all of these are caused by the audio processing callback taking an excessive amount of time to execute. Because the sound card is consuming audio samples at a steady rate, if you don't present those samples fast enough, then you're going to not have anything to actually output to the speakers, and you're going to have some sort of artifact. The constraint that all these audio tools are operating under is going to be known as a real-time constraint. Some people might refer to this as a hard real-time constraint. Some may be soft. It depends upon the exact subfield that you're coming from to discuss this. But all of this is based off of the concept that you have this hard real-time, as in like a wall clock ticking forward, constraint. And if you violate that constraint, then you have problems. In the case of Jack, that's the X-runs. So one of the things out there within code bases is you're going to have some things that can be executed reliably in real time, and you're going to have some things that cannot. Any of the things that can't be executed with regards to that real-time constraint are going to be known as unsafe functions or just real-time hazards. These hazards can be functions that just take far too long to compute. It could be a really complex mathematical computation, or it could be something that involves some sort of non-determinism. Let's say, for instance, waiting for user input. One example of a real-time hazard would be writing to a file. So you could have a function that might call the fwrite call from the C library, and what this is going to do is it's going to attempt to write to a file. It might end up just shoving the bytes in a buffer, but in some cases those sorts of buffers will be full, and you'll have to actually write to disk. And hard disks are a lot slower than just writing a chunk of memory to another place. And that sort of variability in the amount of time this function is going to take is what's going to cause a lot of these problems that can result in X-runs within large applications, well, any size applications. So there's a couple of classes of functions which I'm going to consider to be real-time hazards are just generally unsafe. You have memory allocation routines such as malloc, free, the C++ variants of that, new and delete. You're going to have inter-process communication techniques, some of which might be safe, but a lot of them are not going to be because they might rely on communicating through file descriptors. They might require communicating over network sockets. Any of those operations, especially those that involve file I/O, they're all pretty unsafe because you don't know how long the function is going to take, And it could work 99 out of 100 times, but that one extra time you try it, it could take a couple of milliseconds, at which point your audio system is not going to be particularly happy, and Jack might end up zombifying a client if you're on one of the old versions. It's not really a great situation. Additionally, threading locks. If you have a mutual exclusion variable, you could have the audio thread waiting for another thread to get through some sort of processing. And the thing with any sort of multi-threading is, unless you are extremely cautious with your design, you don't really have a good solid idea of how long it's going to take for that lock to be released. So one of the questions I received when I presented this work in a paper was, how frequent are these problems? So one of the things that I did to investigate that, just anecdotally, previous to doing this, I've seen a lot of projects out there, and a lot of them have struggled with real-time issues in some way, shape, or form. I took a look in a more calculated sense by taking a sampling from the Linux Synths website, finding all the ones that were open source, and doing a quick code review on each one of these projects. And from that, I was able to see some projects had some relatively obvious real-time safety hazards present. And it turns out a lot of them have these sort of real-time safety hazards in the code base in a way that's pretty easy to spot with just a brief code review. Probably on most of these, I spent 5-10 minutes. So why exactly do these problems exist? So hard real-time coding isn't something that is really all that common outside of communities like this. It's a problem that you're not going to find an abundance of resources talking about and discussing. It's something that people aren't necessarily going to stumble across the resources unless they look. And that, combined with the fact that a lot of people in the Linux audio community might be trying to experiment with programming while they're relatively new. If you have a new programmer and they're just learning C++, they're not necessarily going to understand the intricacies of, oh, you're not allowed to use these memory allocation things. You're not allowed to use the standard containers. You're not allowed to use all these standard routines, because they work everywhere else, although the tutorials are going to recommend these techniques, but they don't work well in an audio processing context. So in addition to all of this, the tooling to identify these sort of issues hasn't really been there. So if someone's new and they're learning, if no tool tells them what they're doing is incorrect, they're probably just going to continue merrily on their way. If, for instance, GCC told a user, oh, you're not allowed to do this thing, sent out a bunch of warnings, people would probably correct their behavior relatively early on in the process and learn these sort of problems. But as of right now, there aren't many tools that try to address the problem of real-time safety and trying to identify these sort of bugs. Up to this point, the two primary techniques that people can use are either standard manual code review or some sort of runtime analysis to identify these bugs. For runtime analysis, you could use either GDB or the Jack interposer tool. And in particular, the Jack interposer is a pretty interesting tool in that you have a shared library that you can load up, and whenever unsafe functions such as malloc, free, poll, etc. is called, the library presented by that software intercepts the call, checks what thread it's running in, and then from that is able to either print out some sort of warning message or crash the program so that you can investigate a backtrace. There are problems with both of these techniques, however, which make it really difficult to apply them to large-scale code bases. In particular, code review takes time, a lot of time, especially if you're dealing with a complex C++ project where the overall flow of the program is very convoluted. You could have a lot of operator overloading. It's not entirely clear what is going to call what. So code review is difficult, and it's easy to overlook individual issues. Runtime analysis, on the other hand, while it works quite well, you need to execute the code in order to see a flaw. So if, for instance, you have a synthesizer which You're only going to experience a memory allocation when you're tuning a particular MIDI CC. If you never touch that CC, you're never going to encounter the bug, and the runtime analysis tool is going to make it look like the software is perfectly fine, even though there may be some bugs in there which are very obvious to other techniques. So the fundamental problem here is that bugs can be missed easily. And for both of these other options, they take time. A lot of time to actually use these and a lot of time to cover an entire code base. So instead of looking at these two techniques, the project that I worked on focuses on static analysis. So the project that I produced is Stoat, and Stoat is a static object or static LLVM object analysis tool. And so what that means is it leverages LLVM to inspect code bases and to be able to understand the flow of the overall program. The task that Stoat does overall is broken up into a few different components. First off, Stoat is able to take C and C++ and translate it into LLVM Bitcode files. Each one of these files is roughly a higher level assembly of a sort. So it allows us to take a look at what is happening under the hood without having to really worry about any of the high level complexities of language syntax or anything like that. From those bitcode files, we're able to extract out metadata. This includes information such as what functions are calling which other functions, what C++ classes might exist, how the virtual methods within those classes can end up flowing from one class to another, along with any sort of annotations that people want to insert inline in the code base. And that in particular is pretty handy if you want to use a tool like Stoat in a more long-term situation. From that metadata, we're able to learn what is the overall call graph of the program, and the call graph lets us perform an analysis where we're able to see what functions can possibly be called from some base set of real-time functions. Because if we're able to see that we have a supposedly real-time function call a real-time hazard, then we're able to say we've got some sort of issue and the program might not be reliable in the case where the real-time hazard is being triggered. So what this looks like in terms of real code and how it gets translated along, here we would have a main function. We could have a real-time annotation, which is just going to be a Clang attribute. And here we can see that the main function calls two subfunctions. When we end up translating this to the LLVM bitcode, it ends up looking something like this, which looks like a bit of a complex mess. But we're able to see here we have the main function, and here we have two places where it says that there are calls to other functions, and we're able to see which functions it calls along with some other information which is a bit more helpful for diagnosing stuff on the C++ side, which is a lot more complex than just C calls. From this, we're able to gather simple metadata where we have functions just calling other functions, and this just gives us a directed graph, which eventually gets built up to the full call graph when we integrate all the information from all the different C and C++ files. So originally, I worked on this project taking a look at the Zinad subeffect synthesizer. But that project is a pretty large-scale example to just try to walk people through. So I thought I would take one of the projects that I looked at for the survey of synthesizers, and I decided to take a look at the Helm synthesizer and see what sort of issues could be found there and how Stoat can be easily set up to be run on a project like this. So the first step when using a Stoat is to be able to get those bitcode files. When I first developed it, it was a bit of a painful task, but at the moment it's relatively easy. We have Stoat compile and Stoat compile++, and these basically are just proxies for the Clang compiler. So whenever one of these is run, it runs the normal compilation with Clang, and then it runs a second compilation pass where it extracts out the bitcode files. So that makes it very easy to integrate these things. All you got to do is set the two environmental variables, and you just run make as normal. No real changes to the system at all, as long as it builds with Clang. So went and built Helm, and after that, then we have to come up with some sort of labeling on this code base, because Stoat needs to know what is considered real time, because it's not going to be able to know necessarily this is the function that you're going to pass via a function pointer into another function pointer, somehow eventually making its way to Jack. So we need to label some function. This can either be done in line with the code base, or it can be done externally. In the case of this project, just use the simple whitelist. So here is a function which is a relatively top-level function used in Helm's plugin. And we can just feed that into a whitelist. Once we have it there, then we can tell Stoat to use that whitelist. So it has an annotation for that base function. And then we can tell it to recursively search the current directory for any bitcode files. And since all the bitcode files just end up in the build directory, that means it just goes and finds all of them for us. Running Stoat, it goes along and finds a bitcode file after bitcode file after bitcode file with extremely long paths. And then it's able to run through the full analysis and produce some errors. In the case of the first pass for Helm, we get quite a few errors. So with Helm, like many open source projects, there is a large code base, and it's easy for these sort of mistakes to creep in. For the real-time side of things, Stoat ended up covering about 5,000 functions out of a total of about 50,000 functions. And I'm guessing that probably the majority of that is a juice, which I believe was compiled in with this project. So each one of these error messages is pretty long. So we're going to want to try to condense this a little bit so that we can get more understandable error messages. Stoat offers a couple of ways to help us do that. Skip this slide. So we're going to want to use some of the techniques that Stoat has available. Stoat allows us to do a couple of things with functions. It allows us to either give a whitelist, which tells Stoat that they have to be real-time. We can give it a blacklist, which tells Stoat that they have to be, it tells Stoat that they are not real-time explicitly. Or we can suppress things. Probably the most common use of suppressions is if, for instance, you have some error handling code and it should never execute, which it's always good to verify that from time to time. But when using a static analysis tool, you generally have to tell the tool that those relationships exist. So in the case of Helm, one of the classes that they used is a variant type. So this class could store a number of different things which would vary based upon how it was used at runtime. Since not interested in diving in to verify each one of those uses at the moment, we can just say that we don't care about any function that calls any function that is in the variant class from Juice. And so when Stoat is rerun with that information, it goes through, builds out the whole call graph, finds all of those links, and just removes them. So it ignores that they ever existed in the first place. The next thing we can do is we can use the blacklist. So within Helm, we can say, OK, there's a couple of things that relatively obviously those should not be real-time safe. For instance, loading a patch from disk, saving mini mappings once again to disk, because all those, they involve a lot of string allocations, they involve file I/O, so those should definitely be unsafe. When I performed this analysis, I also added in a couple of extra things, such as I believe std list erase, std list push front, push back. So anything from the standard library that's going to be pushing or moving stuff from containers, because unless you're using a custom allocator, that's going to trigger new and delete, which leads eventually to malloc and free. So none of those are sort of safe things. Once we've done that, we can rerun Stoat. We don't have to regenerate any of the bitcode files because it all has the full metadata. We're just changing the annotations on top of that. We add the blacklist, the suppression list, and this last line here, we can go from a textual representation of the errors to a graphical representation. And that, to me, as long as you don't have thousands upon thousands of errors, that is a much more digestible form of it, at least in my opinion. So let's take a look at what happens when we run this. Oh, 61 errors. That's a lot more like digestible. So we're able to see that it covers many fewer functions, in part because we've suppressed part of the functions that it can call, and in part because we've created these blacklists. So as soon as Stoat finds it's hit something that's unsafe, it doesn't continue looking at the call graph below that. So instead of taking a look at this error, which is a little ugly, let's take a look at another one. So here we have error number 18, and we can see that Stoat is claiming there's a problem with the note on routine within the Mopo voice handler. So here we can see this is the root function that was annotated, and we have the call graph. Process block calls MIDI processing routines. That eventually goes through some virtual tables calling one node on routine, another node on routine, and then lastly we get to this stage. And we're able to see that the problem with this function is within it, we have references to pushing to the front and pushing to the back of two lists, which is almost guaranteed to cause some sort of allocation. If we look at the source code, we can verify that Stoat has actually found a real problem here, because we have the routine, we have the push front, and the push back, and it's found the correct types for absolutely everything. We can, just to be a little redundant, go into GDB, set a breakpoint. We can see we're starting from the jack thread. We work our way up, and we eventually make our way to the note on handler. And we can see, indeed, it is calling the new routine. I believe in this case, some functions have been inlined because optimization between the metadata that's dumped and the normal compilation differs slightly. Now the graphical representation that I talked about before is my personal favorite, and we can see here we've got the node on routine, node off routine. We can see that both of those are dealing with list manipulation. Both of those are going to cause some sort of problems. And we can see how all the functions relate to each other, and additionally we can see when it's grabbing voices, we're also going to deal with some problems with list manipulation. And this is just a very, very small chunk out of a large image, because this is probably showing, since we have 3 red boxes, that's probably 3 errors out of the 61 that was reported a couple of slides back. So what exactly can we say with all of this? We can say that within this project, there are some real-time errors here. We can see where exactly they are, which makes it a lot more easy to fix them than just sitting down and trying to do a manual code review and slowly sifting through things, trying to find that one last thing that you forgot about. In the case of Helm, we can't even utilize Jack Interposer without some change, because it dynamically, or at runtime, finds the Jack library and links directly to it. So the technique used in the other runtime analysis tool can't be applied directly here. So the main thing here is finding the bugs is the first step to fixing them. If you don't know it's a problem, you can't fix it. So Stoat has been used on a couple of projects to help fix these sort of issues. As I mentioned at the start of the project, the original target for Stoat and its predecessors was Xenad subeffects. There were a lot of bugs in Xenad subeffects initially for real-time safety. Probably a couple of hundred initially. A lot of it came down to memory allocation, but there were some stray file I/O operations, some locks. It had the whole gambit of sort of issues. And at this point, I believe it's gone from a couple hundred down to 2 errors. So that's been a pretty big improvement, and still got to take care of the last stragglers, but it's been moving along. There's libRT-OSC, and this is a real-time OSC implementation, and it was built after some prototypes for Stoat had been constructed, and so the API was built with Stoat in mind. So there's a very strict division between which functions are going to be usable in a real-time context and which functions can only be used outside of the real-time context. So that makes annotating a code base like this very easy. In addition, Xenad subeffects uses this OSC library to do internal message translation. So there's probably around 1,000 callbacks within Xenad subeffects, which leads to a lot of function pointers, which generally with static analysis techniques are difficult to handle. But it's possible to extend Stoat to digest metadata and use that to annotate callbacks, even when it's not really trivial to come up with any other annotation-based method. Lastly, Stoat has also been applied to Carla, InGen, and Jalv. So in conclusion, real-time issues are a relatively frequent issue in open source audio projects. And there are tools now to help fix this, both in dynamic and static analysis, thanks to Stoat. And Stoat is hopefully going to help fix some of these issues that are out there for anyone that's interested in investigating them. And Stoat is available on GitHub under the GPL v3. And I'm hoping that perhaps some maintainers might try it out and find a couple of bugs.
Thank you, Mark. Very, very exciting project. So is there any question? I'm sure there are a lot of questions. Yes.
Thank you very much for this tool. We are definitely going to use it. I'm wondering, could you clarify, so we have a main program that loads plugins at runtime. And so there's basically a DLSIM lookup of functions in plugins, and processing functions are called via function pointers. And then there are landing functions in the plugins, so processing functions that I understand we can annotate all of them with annotate real-time or something like this.
Yep.
And question, so how would we tell Stoat that calling the function pointer in the main program should be ignored because it's checked in the plugin? And can we do something like check all methods in derived classes from one class without having to annotate all of the derived classes?
So for the first point, Stoat doesn't actually understand function pointers. So whenever it sees a function pointer and it can't relate it to a C++ class, it essentially has to ignore it because you have to do a lot of data flow analysis to figure out what it could have been. Because for instance, you could have a function where you pass in a function pointer and then you have to track, okay, well, where did that function get it? Oh, maybe you got it from this other function, or maybe you got it from this data structure. And so the end result is it generally just ignores those. So you wouldn't have to worry about that. For tracking C++ classes and all of the dependents, it already does all of that. From the Bitcode files, it figures out what C++ classes there are, how they inherit from each other, and when it finds a virtual method, it assumes that you can either call the virtual method that corresponds to the base class or to any of the derived classes, which in some cases can be a little problematic if you have very mixed real-time and non-real-time code, but that's a bit of a messy design to start with.
So it would be sufficient to annotate the virtual method in the base class, and then it's automatically known to Stoat that all of the derived classes, the same method, should also be real-time safe.
Yeah, so here we can see we have a method. It calls into a vtable method, calls into another. And so every time you see one of these vtable things, that's when it's going through that, and then it sends out extra calls to all the possible implementations.
Yeah, thanks, Mark. Very cool and professional presentation. I was wondering, after the analysis of Helm, did you give your analysis to the maintainer, to Matt Title, and did he plan to implement the changes that you have maybe given him?
I sent it to him probably a week ago, and he seemed to be interested in fixing it. Apparently, I dug up a couple of bugs that he hadn't noticed before, so hopefully a couple of them get fixed with time.
Okay, cool. Thanks.
You talked about build system integration, so that's good. Have you done any continuous integration work with it? Does it? Have you got it going in Travis, for instance?
So you could definitely use it in that context. I haven't used it there myself, in part because you have to generally set up the LLVM dependencies on the machine and then rebuild Stoat every time. But whenever Stoat finishes one line I've trimmed off like right after this is you get a return code. So it's either 0 when it doesn't find anything or -1 when it finds stuff. So yeah, should work there.
If you use the annotations, would it mean if you trigger real-time from somewhere and you don't have an annotation, will it fail that? So if you're in your code, use the annotations to say it's real-time, and you have some functions that actually use real-time stuff but aren't annotated, will it flag those?
No, it will not. And part of that is there's probably going to be a lot of mixed routines, especially, let's say, for instance, you've got a user interface that's trying to display the same sort of stuff that the DSP side is dealing with. So both of those are probably going to share one routine, and the routine might be real-time safe, but it's not exclusive. Though that sort of change to the analysis could be done relatively easily. All of the deductions once you get to the call graph are done in Ruby, so hopefully it's easy enough for anyone to change if they're interested.
Okay, one more thing. So if you have done the analysis, you find like 61 errors, so lots of places to fix. Wonder in what order do you try to fix them? Is there any way to find out, okay, I got many crackles, and most of these are perhaps coming from that function and that
Let's
class?
see if I can bring this up.
A way of prioritizing in what order you want to fix your issues.
So the way that I always do that is the graphical representation. Let's see, do I have it on this machine? I should. Black presentation. Yeah. So we can see that it's a complex graph, but basically you look for the areas where there seems to be a lot of compact stuff, and then you just zoom on in. So there's some of the node allocation routines. We can see up here, this is some of the modulation changing, which is some of the stuff that I initially spotted when doing code review. And basically when you find clusters, that's when you're at the more important stuff. Some of the errors are probably related to all of this, which is all the various sub-effects that Helm has within it. And since they all share similar classes, they all have some base routine, and they all call basically the same thing over here. So some of the errors can be somewhat redundant in that sense. I haven't figured out a way to really condense those per se. But in the visual representation, I think it's easier to navigate that.
Do you have any sort of basic tutorial with the code, or are you thinking of producing something with maybe some simple operation that has 1 or 2 minor bugs which it would show up?
Let's see. I know I put an article on my website a while back, but that was before I had added on the Stoat Compile and Stoat Compile++, which integrated with the build system relatively easily. There might be one on GitHub. I forget. There's a little blurb on how to use it there.
Just one comment. It's certainly a very nice tool, but I'm sort of afraid it gives the wrong impression, in the sense that you can make an app real-time safe by bug fixing it. I don't believe that. I think real-time safety, just like security, comes from good design and nothing else. And once you get at the point where you need a tool like this, I'd say it's basically lost. It's too late to fix it, really. That's not a criticism of your work, because it's really great. It looks great, and it certainly functions well, but as a way of fixing things, I don't think this is the right way.
I think it would be nice if people had done stuff right the first time, but there's a lot of code that people have written.
So I'd like to comment directly on that. I agree that design is essential, but I also envision usage of a tool like this in our build system, so in our continuous integration system, so that usually it runs without errors, and if some new developer commit some code that has that calls one of these problems, we will see it immediately. So this is a usage case that I envision here. So I think it will be very useful for that. And regarding that question, so during the talk I had a look at your GitHub page, and I must say it's good documented, so I could immediately start. I'm not finished yet, but I have a good feeling there.
Thanks.
Yeah, I just wanted to echo that following comment. I work with my entire day is trying to track down bugs in things, and this is invaluable for doing that. It's not so much retroactively trying to fix the problems, because you may have to fix them with architecture, but just to be able to see that I've made a mistake is hugely useful. So I would say thank you very much.
Thanks.
Very good. Well, thank you, Mark.
Yep.